So, can you hear me? Okay, perfect. Yep. First, I should thank organizers for giving me the chance to give this talk. And also, it's very unfortunate that I missed the last 2 days, but I'm looking forward for the rest of the conference. Today, I'm going to talk about error suppression for adiabatic quantum computation, and most of the things that I'm going to talk about also applies to general Hamiltonian-based quantum computation. In some specific places, there's going to be some difference, which I'm going to emphasize. What do I mean by Hamiltonian-based quantum computation? Any quantum computation that I can perform by continuously varying some Hamiltonian, some parameters in the Hamiltonian. For example, whether it's adiabatic quantum computation, holonomic quantum computation, or analog quantum simulation. And the question is, if I don't allow any active error correction, and let's say I don't allow any measurement and feedback, how much error suppression can I get? So I have these limited resources, and we are thinking about these noisy intermediate quantum systems. I just don't want to use too much resources. I want to know how much error suppression can I get. So that's the fundamental question that we are asking. So in this talk, I'm going to talk about some specific type of error suppression using error detection codes. After introducing those, I'm going to talk about their performance in Markovian environment. And also, I'm going to talk about the disadvantage of using this technique. As we will see, the Hamiltonian that we have to implement becomes non-local. And then I motivate using subsystem codes to fight this. And we talk about some examples that we can use the subsystem codes to do things that we couldn't do using subspace codes. And at the end, I talk about some recent results showing that we can have universal quantum computation, both protecting and implementing those using only two-body interactions. If I have enough time, I will also talk about using these techniques using this technique to suppress errors using other type of error suppression, such as random couplings. So let me start. So the first systematic way of using quantum codes to suppress errors was introduced by Jordan, Farhi, and Shor, 2006, and the idea is that if we know that environment, the dominant effect of environment on the system has some specific form, for example, is one local, I target those one local errors and choose a quantum code that can detect the effect of these errors. Then I come up with a Hamiltonian that its ground subspace is protected against this specific type of errors. How should I do that? For example, I can, quantum codes, we can describe them using some stabilizers. Stabilizers are some commuting Paulis, and let's say +1 simultaneous +1 eigenstate of these Paulis would be the code space. So if I just add the stabilizers together, this is one way of implementing a Hamiltonian that has the code space as its ground space. So the idea is simple. I'm constructing a Hamiltonian in such a way that its ground subspace is protected against some type of error. Any error that I'm targeting would correspond to an eigenstate with extra energy, because for those who are familiar with quantum codes, at least there exists one stabilizer that anti-commutes with the error that I'm targeting. So this state would require extra energy. I will be more specific about defining the codes later in the talk, but this is the intuitive picture. Okay, I have some Hamiltonian. I know that I'm protected in the ground subspace, but what about computation? To perform computation, we can encode any computation that we want to perform and replace its operators with logical operators. And for logical operators, I use a bar to show that this is a logical operator, logical Hamiltonian. The property of these logical operators is that they are invariant. They keep this ground subspace invariant. So I don't mess with the information that I have in the ground subspace. So again, I have some Hamiltonian that protects me against noise, and I perform my computation in a nice way in the ground subspace of this Hamiltonian. So here, EP is just a scalar factor. HP is the penalty Hamiltonian, the one that I'm performing my computation in its ground subspace. And HS bar is the encoded Hamiltonian that I'm using to perform my computation. And the question is, how useful is this scheme? For example, how large this EP, this energy penalty should be? Even in the original paper, for a specific Markovian master equation, and starting from some specific initial states, it has been shown that dissipation gets exponentially suppressed both in EP and beta. So beta is the inverse of temperature, which is set by the device. We know that we are working in some temperature, but we get exponential suppression in the EP. And this is basically I'm going to talk about, but I will also talk about show that this is a very general effect in the sense that for general adiabatic master equation, this holds for general initial states, and recently it was shown that it also works for arbitrary time. So let's start from some general Markovian master equation. I have some Hamiltonian for system, some Hamiltonian for bath, and some interaction between system and Hamiltonian. So this is a tensor product between system part and bath part. So this is Hamiltonian on the environment, and this is the environment part of the tensor product. So I start from this. I go through the whole recipe of Born, Markov, rotating wave approximations. I get some master equation. And the only thing that is important here is that the Milad operators in this master equation would basically be Fourier transforms of these A's, the system part of the interaction Hamiltonian, in eigenbases of the system. So pi's are eigenbases of the system Hamiltonian, and this Milad operators would be in this form. This was shown by Tamim, Sergio, Daniel, and Paulo. For example, this is the specific Markovian master equation that I'm showing here. And what's the quantity that we are interested in here? Let's say we are thinking about population in the ground space. For example, we are performing some adiabatic quantum computation. We want to know how a good quantity to look at is how much excitations do I get. So here I'm looking at the initial time. I look at the population. Pi0 is a projector to the ground space, and I ask how much does this change with time. And the important thing here is that I choose the code that can detect these A's. This A was the system part of the interaction Hamiltonian, right, in the previous slide here. So I plug in, and what I can see is that after some algebra, I get some equation for the rates, but this is the important part. The only energies that show up that contribute to this excitation rate are the energies that are out, are the levels that are out of the code space. They are in C perp, they are not in C. So the only way that environment can excite the system is if it provides enough energy to excite us to the outside of the code space. It can't produce evolution inside the code space. First, it has to give us enough energy to go out. And by construction, we know that this energy, because of this penalty Hamiltonian that I described, by construction, we know that this is bounded by something proportional to EP, which we are enforcing. For example, to be more to talk more about details, let's say if I'm in some thermal environment, and let's say KMS condition holds, and then there's this exponential relation between decay and excitation in the same energy. Just plugging in, we can easily see that the excitation rate gets exponentially suppressed up to some polynomial corrections. Again, the message here is that with increasing the size of the system in a constant temperature, the EP, the energy penalty that I have to provide, just goes logarithmically in n. Okay, I mentioned this, I talked about Milad operators, but really it's more general than that. We can think about double-sided Schrödinger equation, other master equations that are, for example, we can avoid problems with rotating Weber approximation. And also, this phenomena is more general. In a recent paper by Daniel, he showed that this works also for arbitrary time. Okay, so we have this exponential suppression, but what is the cost? So why should I be concerned about implementing this scheme? One specific thing that I'm going to talk about in the rest of the talk is about locality of the Hamiltonian. So the recipe that I mentioned was, rather than implementing the original computation, I wanted to encode it into a new Hamiltonian, and this new Hamiltonian, by construction, can be more non-local. What do I mean by local? For example, I say 2 local when I have 2-body interactions, 3 local when I have 3-body interactions, and so on. And even if I don't want to perform any computation, it's just a quantum memory, no quantum computation, in the original paper, it was already shown that using the regular stabilizer codes, I need at least 4 local Hamiltonians, which I assume experimentally we don't like them. We prefer to work with simpler things to implement. Okay, what about 2 local Hamiltonians? What can I do with them? Can I go beyond this 4 local Hamiltonians in this specific form to come up with an error-suppressing Hamiltonian? Again, it was shown that 2 local commuting Hamiltonian, which is a generalization of this subspace stabilizer codes, still I can't get error suppression. But like at 2017, Jiang and Riffel, they showed that using some specific type of subsystem codes, which is a generalization of the stabilizer codes, we can have a non-commuting 2 local Hamiltonian that can suppress local errors. And that's the motivation why I will be talking about subsystem codes. Okay, to be more formal, let's briefly talk about quantum codes and subsystem codes. So let's say subsystem code in a stabilizer formalism. Again, I define a code in a stabilizer formalism by defining some commuting Paulis, here S, and this would define my code. The +1 simultaneous +1 eigenstate of all these Paulis would define my code, and any error that anti-commutes with one of them would be some error that I can detect. The rest of the space, I can define my logical operators in it. So I will have logical qubit 1, logical qubit 2, up to any number that my space allows me. As you can see, I mean, one can prove actually that in this formalism, you can always make these logical operators to come in conjugate pairs, meaning that operators with the same index anti-commute and with different index commute. So we can always write them in this canonical way. Subsystem codes, we can just think about having the same code, but ignoring some of the logical operators. So here I'm saying that I don't care about these logical operators. If error basically hits this part, I don't care. I only care if I can suppress error or have the information in this part. Because all these operators commute with all these operators, this introduces some tensor product. We can think about That's why we call them subsystem codes, because it becomes a system tensored another system. And I mean, that's the name subsystem coming from. And to define a code, rather than now only thinking about S, the stabilizers, I have to both think about the stabilizers and the gauge operators. So that's how I define the subsystem code. It's now a non-abelian code, so this generating group is not commuting. So it's a generalization of the previous code. Given this group, all the properties of the code, the errors they can correct, detect, we can just list it using this G. And one extra definition, which hopefully will be the last part of the technical things, is that I want to differentiate two different logical operators, bare logical operators and duress logical operators. Bare, any of these logical operators in this picture, in this box, I'll call them bare because they commute with all these operators here, and of course, always with this. Duress logical operators, as I mentioned, I'm saying that I don't care what happens here, right? But I care what happens here. X1 itself would be a bare logical operator, but X1 times some operator from here, any operator from here, would again act like X1 here. So it is a logical operator that I want, but doesn't commute with operators here, right? Because it has some operator, let's say Z2 bar from here. So anyway, the bare version of the logical operator, I just get it from here. I can have it dressed with some other complicated operation on the gauge group, gauge operators. This it comes into my talk in an unexpected way, maybe, but later we'll see. And okay, why should I care about subsystem codes? This generalization. It's very interesting that these codes are more powerful when we have some spatial locality constraint. So there's this nice paper by Bravi. He shows that with subsystem codes, we can achieve rates that we can't achieve using ordinary subspace codes if we have some spatial locality. Okay, so given all this story, the way that we can come up with another way of encoding Hamiltonian is to, as before, encode the Hamiltonian now using bare logical operators. But this Hamiltonian that I mentioned that we want to construct to have the coded space as its ground space now can be non-commuting because I can build it using these generators of this group. It's a non-commuting group. So I construct this penalty Hamiltonian using any element of this. So this is generalization of the previous construction. So again, but the picture remains the same. I have some Hamiltonian. Now it's more complicated. It's non-commuting. It has the coded space in its ground space. I'm guaranteed that any error would excite me to some excited state. And I perform my computation using bare logical operators as before. And I know that it doesn't infer with, I can perform my computation in this coded space without messing with anything. Okay, so now let's look at some, hopefully, pictures. Let's look at the easiest, the smallest code possible. So I want to encode, I want to use 4 qubits to encode logical qubits. As you can see, there's already enough room to encode 2 logical qubits. This is qubit 1 and qubit 2. As you see, these 2 operators, x bar and z bar anti-commute, x prime, z prime anti-commute. But these together, the operators here, everything commutes. So this is properly, I'm defining 2 different logical operators. I'm encoding them in 4 physical qubits. But as I said, we will say that, okay, I don't care about one of these qubits. I don't care about these primes. I only want error suppression in one of these logical qubits. Okay? So the gauge group, this non-commuting gauge group, I will use these operators that I don't care about, plus the stabilizers. That would be the gauge group. I can simplify it like this. And I can use this to construct my qubit, my logical qubit. If I depict XX interaction with a blue line and ZZ interaction with a red line, the penalty Hamiltonian that I have to implement, it basically looks like this. I only use two-body interactions on 4 qubits, and I'm guaranteed that we get full error suppression for one local errors using these 4 qubits, only using two-body interactions. So it's important to emphasize that this is something we don't get using subspace codes. We can prove that we can't get this using subspace codes. What are the logical operators? X1, X3, which is basically this, and Z1, Z2, which is this. Okay, so at least we get error suppression for one local errors. How about performing the computation? Of course, one idea would be to use 2 blocks of this and use 8 qubits, right? And then penalty Hamiltonian, again, would be this and this. Everything's 2 local. Again, I have error suppression against any one local error, so that is good. But what if I want to implement some logical operator? Whether it's universal quantum computation or whether it's, let's say, any two-body interactions. Let's say I want to encode the penalty Hamiltonian in D-wave. At the final Hamiltonian, I have two-body interactions. Now, using this scheme, I want to protect it against some error. It has ZZ interactions. ZZ interaction in the logical domain would correspond to a 4-body interaction when I want to protect it, right? So still I have this problem for computation, that I need 4-body interactions to perform either universal quantum computation or any useful quantum computation. But we can be smart and come up with more complicated codes. So, for example, one example is actually this one. It's just a chain of ZZ interactions, and I put some X, local X, on this chain. So this is the Hamiltonian that I want to both implement and protect against one local errors. Rather than to do that, I come up with this ring rather than chain, and I put this XX and ZZ interactions alternatively. So there's blue, red on these 2n qubits. This would be my penalty Hamiltonian, and switching between X and Z, this would be my the logical Hamiltonian that I have to implement. So again, it's a ring, only 2-body interactions. I can both implement and protect a chain like this. There's a caveat here that how about the gap of this penalty Hamiltonian itself? As I mentioned, the idea here is that we are focusing on the gap of this Hamiltonian so that whenever there's some excitation, we know that the environment has to at least pay some amount of energy. This Hamiltonian itself can be gapless in general. For example, for this system, we can show that the gap actually decreases as 1 over n. And therefore, the penalty that we have to provide has to grow linearly with increasing the size of the system. But to give you the context here, we should compare this decreasing gap of this penalty Hamiltonian, and we should compare it to the gap of the computation, to the case that we don't want to protect it. We know that in general, the gap of computation can decrease exponentially. Even for chain, for those who are familiar with this story of the chains, for example, there's this alternative J1, J2 chains that the gap of its gap can close exponentially. So here we have this 1 over n gap versus exponentially decreasing gap. So we still have good protection against noise for the systems. But this is a very limited Hamiltonian, right? So what can we do with this? This is already universal for Hamiltonian quantum computation. In the sense that if I allow, even if C, this, rather than having time dependence here, I have some constant C. If I allow to Ci, these couplings, to change rapidly, this becomes, we can perform universal quantum computation using this. But this is not the ultimate goal that I want to have in this conference because I'm thinking about ground state computation, adiabatic quantum computation, and this Hamiltonian cannot perform universal adiabatic quantum computation because, of course, it's a chain with transverse field. And one easy way to see this is that I can always make this a stochastic, so it's ground state is easy, and I can perform universal quantum computation in the ground state. So what can I do? Can I go beyond this chain? No. So we can prove a no-go theorem showing that if you insist on using bare logical operators, you can't go beyond chains. In the sense that if you want, let's say you have one specific node, Z1, here just focus on one qubit, like qubit 1. I have interactions Z1, Z2, Z1, Z3, Z1, Z4. So the degree of this node is 3. And let's say I want to have also X1, something that anti-commutes with Z1. We can show that using bare logical operators, these logical operators that commute with all the gauges, I can't do this. We can prove that. Actually, we can prove it for more general CSS codes. CSS type, I should say, CSS type subsystem codes. This I can do. And intuition of the proof is simple. This requirement that I want, which is having gauge operators of weight 2, basically after some argument, it basically means that these operators Z1, Z2, Z1, Z3, Z1, Z4 can't overlap on the physical qubit. They should have disjoint supports. And because X1 has to anti-commute with all three of these, it basically means that trivially it can't be too local. It has to be at least 3 local, so it intersects with 3 of them at different places. So that's basically the intuition of the proof. This is also basically independently done by Lizonek, Roy, and Trandafir. But we can go beyond that using gauge operators. So with bare logical operators, I can do that. But the good news is that with dress logical operators, we can. So we can come up with this code that encodes 2k qubits into 6k qubits and has, with 2-body interactions, I can implement gauge operators, single qubit logical operators, and product of any 2 logical operators of the same time, XX, ZZ, or YY, up to a gauge freedom. Why should I care about this type of Hamiltonian, meaning XZ, XX, ZZ, or YY? Because we already know 2 different schemes that use these interactions to give us universal quantum computation. One is the perturbative construction by Beaumont and Love, which uses XZ, XX, and ZZ to generate universal quantum computation. But if we don't like perturbative gadgets, I guess on Tuesday, Alessandro's talk, unfortunately I wasn't there, but there's this construction by Seth Lloyds and Barbara Terhall, which use XX plus YY and ZZ and Z, and that's already universal for adiabatic quantum computation. This is basically the hopping term that we have there. So this set of interactions are enough for universal, and that's why I'm targeting that in this code. So how does the code look like? Let's say I have some 2k qubits. I add 2 qubits on the 2 sides. And XX and Z, I again depict XX interaction with blue line, and I use orange line for ZZ interactions. These would be my logical operators. X1 you can, by eyes, just check that this anti-commutes with this, but this commutes with all the operators here. So this is logical operators in a canonical form. Gauge operators on the same set of qubits would be this XX and ZZ interactions. Okay? After a little bit of calculation, we can see that the stabilizers and stabilizers of this code are non-local. So they are on all the 6K qubits. But the gauge qubits that I have to implement are 2 local. And that's that's the important part. It also has this interesting feature, which is an X interaction on this is equivalent to this times this gauge operator, right? X equals to XX here, XX here, XX here. Basically this. And this is how I'm implementing 2-body logical operator using 2-body physical interaction, right? A 2-body physical interaction on this 2 is equivalent to a 2-body logical operator up to a gauge. I have this XX interaction as a gauge. This is not only for 1D, I just presented like that because it was simpler, but we can have the same picture in 2D. Some properties of this code, the way we construct this was using this Brawley's generalization of Bacon-Shor code, but we also noticed that this can be related to a code that was proposed by Ganti and Quarters. Basically, we can think this as a subsystem version of Gutsman code for those people who are familiar with, but it's not important here. A geometrically local Hamiltonian using this construction would be mapped to a geometrically local Hamiltonian. This is a property that we want. Again, another thing is that, again, this Hamiltonian is non-commuting, so its ground properties are complicated in general. But we can show that it has already actually been shown that some of the ground state of this non-commuting Hamiltonian, because it's stochastic, we can prove that it has the code space. It is inside the code space. This is a more general result by Burton, actually, but it applies to our construction also. And again, one thing that I want to emphasize here, that this model is related to the quantum compass model that people have been studying in condensed matter physics. There are a lot of numerical results about the gaps of different versions of this Hamiltonian. One thing that I want to mention is that because I'm using the rest logical operators here, I have to go beyond what I was describing in the previous scheme, which was saying that the Hamiltonian that performs computation commutes with the Hamiltonian that protects me against error. Here I have to go beyond that, because when I implement this 2-body interaction, 2-body Hamiltonian in the physical level, these gauge operators would be important. They will show up. And if they don't satisfy the right properties that we want, this would be a problem. But what we can show is that when we are constructing the penalty Hamiltonian, we can make sure that these gauge operators in the code space have some trivial effect. So there's some, let's say, some shift in the energy. Then I can compensate for their effect in the ground state by just renormalizing the coefficients that I have to implement. So I can compensate for the role of these gauge operators by just rescaling the coefficients. Just as a recap, we were talking about implementing this Hamiltonian. We said the idea is that I want to protect against some type of errors. I want to also perform my computation. We started by saying that if penalty Hamiltonian is commuting, we can't have error suppression using 2 local errors, 2 local interactions. If we allow HP to be non-commuting, we can suppress errors. But if we still want this 2 Hamiltonian to commute, we can't have universal AQC using only two-body interactions. But we can go one step toward non-commuting. Not only HP is non-commuting, let HP and HS be non-commuting. And then we can see that we can get universal AQC and suppression of local errors. Okay, so till now, I've been talking about different things that we can achieve using subsystem codes. Now, very briefly, I would like to broaden the picture a little bit and talk about more general subsystem codes. Quantum Zeno effects. The whole thing that I've been describing, we can think it as a Zeno effect in disguise, because a very strong interaction is basically equivalent to performing some measurement. What do I mean by that? Let's say I have some Hamiltonian, and I give it some very large factor behind it, and I look at what's the effect on some noise or some general Hamiltonian. Just looking at the first order perturbation theory, we can see that the effective Hamiltonian here would be this noise or any Hamiltonian that I'm adding here, but conjugated between eigen projectors of HP. So any Hamiltonian, when I increase this EP, will be projected into eigenbases of this Hamiltonian, right? This is just first order perturbation. But if by construction I know that eigenstates of HP are related to the coded space, this is basically like saying that I'm projecting this noise into a measurement that is performing quantum Zeno effect, right? In a quantum Zeno effect that is basically has coded space as one of the eigenprojectors and other eigenprojectors. This is one way of doing this quantum Zeno effect, performing this. But if I have extra resources, I can think about other ways of doing this. One way is to just, rather than implementing these stabilizers as Hamiltonians, I apply them using unitaries, fast pulses. So this is some extra resource that I allow. I say that, okay, at very short intervals, just apply these stabilizers as unitaries. And if this is happening very fast, the effect is exactly like having a Zeno effect again, and we get error suppression. So this is the second way that we can think about dynamical Zeno effect, which is using dynamical decoupling. But the last one that, we are thinking about it is, what if these coefficients here are random? So rather than having fixed EP, I have some random fluctuations on this energy penalties. Again, we can show that. So the idea is, rather than having some very large AP, I have some randomness on this AP. And what we can show is that, but this is a very simple example. We can show that this is always, this is exactly like a Zeno effect again. So let's look at this quantum channel. Actually, this is my last slide. So I have this quantum channel. I implement some Hamiltonian HP with some strengths. And this strength is random. I can just, by looking at this, we can decompose it in eigenbases of HP. And we can see that it already becomes, again, as a measurement plus some correction. What is this correction? This correction is related to the characteristic function of this random variable EP that I'm defining, right? But already it's an approximation of a Zeno effect. For example, if this is Gaussian random variable, this would be exponential, and we have some exponential suppression of off-diagonal elements of rho by just this randomness, right? So this is a third way of implementing quantum Zeno effect when we want to have error suppression. So to summarize, I just want to say that there are different ways of implementing this quantum Zeno effect. A systematic way of that is using quantum codes in either of these, whether it's dynamical decoupling, whether it's error suppression, or is it randomness. And I guess that's it. Yep. Thanks.
Okay, questions?
Very good.
Hi, Milad.
Hi.
So previously, I got a question about the dressed logical qubits. So you have the gauge operators dressing there. It was there. No, beyond.
Here?
Back. At the end of the all too local, when you have the dynamics with the dressed logical operators, and you have the dressing by the gauge operators here, yes. So those gauge operators change with time, right? During the adiabatic anneal. Their definitions will change with time, so I'm a bit...
No, so these G's
Yes.
are time independent. So similar to here, similar to, let's say, let's go somewhere that I have it in notation, proper notation. Okay, here. So here, for example, this is the construction that we are using, right?
Yeah.
So HP is time independent. It's a fixed penalty Hamiltonian. I just build it once in my device, regardless of the computation that I want to perform. So it's fixed. And then I perform my computation, which is a time-dependent operator, and that's independent of the gauge operators.
All right. If they're independent of time, then it's fine. Yeah. I was thinking from what you talked about before, when you mentioned this, that the gauge operators are time dependent, and then you wouldn't be able to compensate by just rescaling the code.
That's a very good question. So, which I didn't have time to talk about. Actually, that's important. So, it's important. This is super important, as I guess you're pointing out, that these are not only time independent, also these are computation independent, meaning that this construction should be, this compensation that I want to provide, it should not depend on the computation that I want to perform. Otherwise, it doesn't make sense. The computation might be so hard that just finding these coefficients is. But this is super important that these coefficients are independent of the computation. So in principle, I can just run it on my device without performing computation, just as a quantum memory, measure these gauge operators, find these alphas, and now recalibrate any computation that I want to perform.
Okay.
That's a very important point, actually.
Okay, very good.